All right. It seems like it's a relatively quiet class so far. Got a small group today. I like that. By the way, those of you who aren't here, no, I'm just kidding. You're my favorite students. Just kidding. No, actually, there's no problem not missing class. None. And you know that. That's totally cool. We're all adults here, and I try to make it. Does not harm your grade, does not harm your impression of me or anything at all. So, what's new? Sunshine. Yeah, no kidding. Maybe that's part of it. All right. So, a couple heads up. Sorry, I'm sitting down today. I'm going to lecture sitting down because I'm lazy. That's what happens when you become full professor, right? You just become really lazy and really absent-minded. Never thought I'd get old, but sure enough, it happened this year. So, a couple things about me, or about things I've screwed up. Let's just make this about things I've screwed up this week, all right? Your homework system, I mentioned last week how when you submit it, there's a couple of things wrong with it, and you're going to be assessed late points because I couldn't change it. All that will be fixed, and I'll email you when I fix it and update it, okay? Because, again, the reason why I can't fix it live is because if you're currently doing the homework and I go in there and change the database, it will kick you out and not save your answers. And I thought it would be better to not have that happen than to risk the chance that I might have had it happen to a couple of you, but for the better good. No, I just thought it would be better to do that. We have such a, for me, it's not a large class. Some of you may be teaching larger sections in your GTA work right now. But for me, for the grad level class, it's a sort of a big class. And so I'm not used to having the logistic issues on the database side. Part of that's also because the technology I use for it is just ancient in technology terms. It's like nearly 20 years old. So yeah, it's like using your I don't know if any of you have a calculator anymore. Do anyone have a calculator? Yay! Good job, Becca. Is it a TI?
Yeah, it is.
That's nice. I was going to say, it's probably one of the newer ones, though, not the ones I went to school with back in the day. But yeah, it's kind of like using that for like, that's the only thing you have rather than your laptops in class and everything else. So again, I apologize. I know this class quickly becomes what I screwed up this week, but that's that. The next couple bits of information are today we're talking about matrix algebra, another reason why people may not be here. It's a good subject, though. And then we're also going to talk about the multivariate normal distribution. So we're getting into multivariate statistics. Next week is spring break, so do not come to class. I will not come to class, but I'm not going to announce that class is canceled. So we'll see who shows up. And actually, I won't even know who shows up. I may be in the building. Maybe I'll peek my head in. Hey, no classes. I doubt that. I think that's one thing you have circled on your calendar. No class online either, but what I'm going to do is I have a couple lectures I'd like to prepare between now and the next class, and I'll put them online. But given the way things work, I hope to have them up there by the end of Friday. I don't need you to watch all of them over spring break, but just try to start watching them because they're going to relate to the next homework, which we'll talk about when we come back in the beginning of next class. It's about multivariate models. When we start multivariate models, we're going to use a package called Lavon in R to do this. Lavon is nice because it provides direct modeling of each dependent variable, which is very helpful. You may not find it nice, though, to begin with, but believe me, it will get worse. So, syntax-wise. But it's not to make it bad. It's just we have issues with people writing syntax. So we'll start there. The next homework will be out starting on the 27th when we come back. So you don't have any homework to think about. There won't be a quiz between now and then either. I'm not going to quiz you on this stuff. I would like to watch the lectures so you're prepared to know what's going on. And again, those may happen. They'll be up by Friday. I'm hoping to have them up tomorrow, but they'll be up by Friday. So you should be able to watch them hopefully a little bit, maybe the Monday before class. I don't know. Anyway, but you won't be quizzed on them. But do please watch them so you're prepared to talk about what homework looks like when we get back. Other questions or thoughts? Oh, no. It's very quiet today. It's very interesting. let's see what I was going to do. What else was I going to say? Whoops. Just want to make this bigger. I'm going to give lecture today on the iPad so I can draw. There. Now you can see it. That looks fairly decent, right? Okay. Shall we begin the punishment of matrix algebra? How many of you have taken a matrix algebra class before? The math people. Or can I call you a math person? I don't know. You might be a math person. I've forgotten which program you're in. I know Jacinta's background. She's an advisee of mine, so math people. I shouldn't say that. I'm a math person now. No, matrix algebra is one of those things where you might be learning this and thinking, why do I need to learn this? Why are you putting this in this class? Well, I'm doing it strategically because when you get to multivariate statistics, when you get to a lot of statistics, particularly when you start trying to understand what comes out in a user manual or a user guide, you quickly run into matrices describing what's going on underneath the hood of the software. Really, really quick. And so my goal in teaching you matrix algebra is not to make you people who do matrix algebra for a living. It's more to help you try to decipher what's going on under the hood a little bit. Because what I found is if you can just play with some numbers, you get a fairly decent mental representation of what's happening, and I know each of you is capable of that. You're actually all capable of matrix algebra. The question is whether you want to learn it. But the bigger picture is I'd like for you, when that next method comes out, the one that none of us have heard of yet, that's going to be the next AI or the next whatever buzzword that you're going to use. I don't know if you have any buzzwords that you use, but you know what I'm talking about, right? The next machine learning, or whatever someone's going to say, hey, you need to do this to do research in your field, and there's matrices involved in it that you can cut through the BS and be like, yeah, that's not really different than what they did last time. Does that sound good? Also troubleshoot what you're doing. You also probably want to have an idea what the model is doing as well when you use it. So that's the goal. It's the thought. So we're going to start with matrix algebra. Again, it's not, the goal of this lecture is not to give you, is the screen okay? I mean, it cuts off a little on the sides, but there's usually nothing there. Is that going to be okay? Visualize? Cool. This is not, again, this is not the deep dive of the whole, like you can take semesters worth of matrix algebra, and I'm going to do this in like half of the lecture, right? So just bear with me if you don't care to hear this. I do hope you see it has a point. I will make this one point, one last one. Matrices do a great job simplifying equations for us. You may not believe that when you start to see them, but how many of you have ever taken a stat class where you had to memorize an equation? Yeah? Did you have to memorize what the intercept was in a linear model? But at one point, or like the slope? Yeah? Okay. What if I told you, so that was, you probably have this equation that has a sum in it somewhere and whatever else, right? You've been there, you've seen these before, somewhat. Many people have. When I taught, I don't like the memorization approach, but I sort of joked about it when I taught a class back in 2007 over in the psych building. And I told my students, if you learn matrix algebra, the only equation, I'll only have you memorize one equation. Just one. If you know matrices, one equation will tell you the formula for the intercept, the slope, whatever you put in the model, interactions, nested effects, whatever, one equation. And I kid you not, up in my office, I was leaving that year, and I always joked that I would like people doing other activities in class. I always said someone doing cross stitch would be kind of cool. And there was someone who was like doing needlepoint in the back. Well, what she was doing, she was making a shirt for the bear that had this matrix formula on it. The one they had to memorize, that's it. So the reason why I'm telling you this is I'm not going to make you memorize this formula. But back in 2007, I said, all right, how about one formula, just to make a point? And the point is that the reason why matrices exist is that we can simplify a lot of that notation that you have to go through into one very streamlined form. It's just really compact. And understanding that compact thing is important to understand what's going on underneath the hood of the software, to understand what you're doing with your model. But that it's actually a lot, like once you start to understand it better, you start to see it as a little bit more simplistic. And the same form shows up over and over and over and over again. So that's my goal in trying to get this to you. Cool? So it'll simplify, equations. So whenever you have a student in your program, and they're in one of the classes that you took where you had to memorize that, give them this formula and see what the instructor says. It'll freak the instructor out. It's like, no, I got it all. Here it is, right here, this formula. Actually, you want me to give it to you right now? It's a secret. All right. If you have a set of betas, any betas, I'm going to put these like this. Take the X matrix. The little half arrows above indicate matrices. This is a matrix inverse. X is the matrix where you put your predictors. Y is the matrix of the vector of your data. And this thing, X transpose X inverse, X transpose Y, is the equation for the least squares regression line that you do in everything that you've done with a linear model to this point. So that class that a couple of you have noted that you had to memorize the slope formula for, or the intercept formula for, it's all embedded in this thing right here. This is more general than all of it, and that's all there is. I've got that as a tattoo on my shoulder. Maybe not. Okay. No, my generation was the last to not get tattoos. So me having gray hair and balding, I need to maintain that. If they could tattoo hair, though, never. All right. So why learning a little bit of matrix algebra is important? It's really the alphabet of statistics. There are people who've argued that before we really did matrix algebra well, without that alphabet, we weren't really able to better understand statistics, to do them in a large, as well as we've done historically in the statistics fields. But really, it becomes, just like statistics itself, I always think of this class as another language on top of, however many languages you already know. For me, it's one. Thankfully, I speak statistics a little bit. This itself is the reason why we're able to do more complex things in our research. So, for example, imagine you're interested in analyzing some repeated measures data. But things don't go as they should be planned underneath there. So you go to one of my favorite documents. Let's imagine you're using SAS. And in SAS, there's this procedure called proc mixed. And proc mixed is the mixed model formulation of a repeated measures analysis of variance. It's pretty complicated, but this is what you read in SAS. This is the help guide, right? What do you see littered in it here? Okay, that starts to look like your regression line, but that doesn't look anything like that. There's no beta 0 or beta 1 or whatever else, right? And there's these boxes of things, and then there's this, what? Huh? Or this V, that looks like the absolute value of V. Right? All of that right there is part of the matrix language that you have to learn to see how this works. And sure enough, if you look really, really difficultly, that equation I just put on the last slide is actually right here, although it's got a V inverse in the middle of it right there. So this is sort of part of why you need things in matrix algebra. Nearly every one of our multivariate statistics techniques uses matrix algebra to describe it somewhere. If it's not in the R help, which again is help, right, in quotes, it's somewhere online in their vignette. It's somewhere there. The people who are creating the packages are generally using matrix algebra. The GLHT function that you use, that has tormented me over its p-values for some reason, but GLHT uses matrices, right? And that's why whenever you had to put the ones and zeros in the box, if you noticed in there was, on the outside of all that, there was the function called matrix. You were actually forming a matrix, and you needed to put them in that order because things have to line up when it does a matrix product that we're about to talk about in just a moment. So typically you see matrices in statistics journals. You see them in pretty much anywhere that you're trying to use the software. So it sort of need the language to parse your way through it. It's really cool because, again, it makes technical writing more concise. Instead of having 18 equations to do one thing, you can usually bottle them up into one really scary-looking equation, but something that works. So here, this first one right here, I just wrote that for you. X transpose X inverse, X transpose Y. That's your least squares regression line. That's your formula to find it. This, down here, that one looks pretty terrible, doesn't it? lambda phi, lambda transpose plus psi. Have you seen that one before? Ahmed has.
906.
What's that? 906. That is the covariance matrix that is implied whenever you run a factor analysis. That right there, where lambda is the matrix of factor loadings, phi is the matrix of factor covariances, and psi is the matrix of unique variances for your items. So all that starts to just become, when you start to use this more and more, it literally starts to read like an alphabet. You say, oh, you start to see this over here, you start to see that over there, and you're like, I can kind of make sense of things. It just takes a while to get there. So we're going to unpack how to read this today. Another thing I want to help you with is that this is great if you are in a boring conversation or an awkward moment. Really good to help someone just to jettison it. You know, like someone's talking to you and you don't want them to, and they ask you some type of question, you're like, you know, I'm really having a hard time thinking about that because I've got this matrix algebra problem I'm working on, and I'm really trying to understand why the determinant of a matrix involves a bunch of submatrices. Usually that shuts people down. I have used statistics for my benefit before, usually on plane flights. You know the person you know that person, right? You know who I'm talking about? That person just wants to know all what you're doing. Oh, I do statistics. That usually scares them off. It's like, oh yeah, I do dentistry. Oh, shut that down. And then, oh, that's great. No, I really love drilling out cavities. You know, like something that's really like, no, I work in sewers. The things to shut it down. Statistics is right there with it, right? Although I have had, I was on one plane flight and someone's like, oh, I know statistics. Yeah, I'm into that. And it was like, you like baseball cards, right? So, all right, that's fine. I couldn't just stop that. Or there was one, I was at a bar with a friend and used this trick, and the person says, well, I'm a PhD candidate, and I actually have some stat questions. And I was like, dude, like we were like trying to get a break from this, and this is actually a long time ago out at Johnny's on the west side of town. And this guy got angry that we wouldn't answer his stat questions. Like so mad that we were like, look, we're just gonna leave. It was like a bar fight situation. Like, but other than that, statistics, it works really well. Just get out of the conversations you don't want to talk about. And matrix algebra is one of them. Although unless I'm that guy on the plane next to you. And oh, really? Tell me about the eigenvalues. So let's do some definitions real quick. I didn't go to Wikipedia this time. I did dictionary.com because where I want my free information, I need to see what's better at giving what. A matrix is a rectangular array of numeric or algebraic quantities subject to mathematical operations. Boy, that sounds mathy enough, doesn't it? It's a box for numbers. That's a matrix. You put numbers in the box. And when you got a box full of numbers, and you got another box full of numbers, sometimes you can combine the boxes. That's what matrix algebra, that's how it works. Cool? All right. It's also a substrate on or within which a fungus grows. So you can see where this is going, right? That's one of the definitions. So we're going to talk about fungi. Fungi? I don't know. Anyway, in class here. Then I had to look this up. So I have a great big fat F in Algebra 2 in high school. I sort of wear that as a badge saying, hey, if I failed math before and I can do statistics now, then anyone can. Yeah, absolutely.
You mentioned this before, but what turned you around from excelling?
I took statistics to get out of a math requirement in community college. Thank you for asking. So I was in community college. It was my second semester. It was my first semester. I somehow survived the college algebra, and then to get a degree, to move on from community college, I needed either business calculus or statistics. And I'm like, oh, I know which one I'm picking, right? And so I picked statistics, and I just fell in love with it. It was like I had math had a purpose, whereas I knew I had great teachers in high school. This was not on them. It was just this awkward social situation, and just I was a shitty kid. I think I could just say that. Still shitty, just no longer a kid. But that's But no, it was more it was more just, I was like, wow, I don't know what I want to be when I grow up, but I want to do this in some way of it. And so I started doing as many math classes as I could. By the time I was a senior, I was finally in calculus 1 and 2, or 2 and 3. Actually, no, a junior. I took calculus my junior year, but then senior year I was able to do statistics minor in school, and I thought that would help me because I finally settled on doing some type of social science research. I enjoyed psychology and whatnot, but I thought statistics would help me achieve those goals a little bit more, and so that's where I went. So yeah, it was statistics that enabled me to be here in front of you today, but not matrices. So thank you for asking. But yes, I have an F in algebra, and I wear it proudly. And because I didn't exactly remember, like if anyone stopped you on the street and said, "What's algebra?" would you be like, "Oh yeah, algebra, here's my definition." So I had to look up the definition. Maybe Jacinta, you might be able to define it, right? No, maybe. Anyway, but a branch of mathematics in which symbols, usually letters of the alphabet, represent numbers or members of a specified set. All right, so I remember this. I'm seeing this in my daughter who's going through introduction or algebra, first algebra. She's in middle school in Alabama. Do you ever remember your first encounter with algebra and you saw like y equals x plus 1? I'm like, x, yeah, x is the next letter in the alphabet, right? If x plus z would be equal to x plus 2, right? Or something like that, right? Like I just didn't get that letter was a placeholder for things. I was just much more literal about that. So that's part of algebra here. The matrix is a placeholder for the box of numbers that we have. And then after that, we have these placeholders are used to represent quantities and to express general relationships that hold across all the numbers, right? At least numbers in that set. Well, for us, it's like numbers that are real, like the things that we work with, right? So what we're going to talk about is symbols representing boxes of numbers now, not just one number, and properties of these boxes that hold for any box of numbers that you could put together that involves what we're going to work with in data, which is usually real numbers for the most part. Sound cool? All right. Then on top of that, it says together a set together with a pair of binary operations. What are those? Like addition. Take two things and put them together. Subtraction, multiplication, that type of work. And so therefore, you put the idea of these symbols representing any possible number, and you put together these operations that you can do on it, and now all of a sudden you've got the whole language. The alphabet is the symbols, and the operations is sort of the grammar of the language. And you put it all together, and now you're talking about what's going on with matrices. So, but yeah, it is very abstract from many of the purposes in this class, and I'm pretty sure it's abstract from almost every one of your programs of study in graduate school. Again, save for a handful of you, or a very select number of you who are my advisees in this class. But even then, that may not be the purpose that you're here either, and I totally appreciate that. So, not to scare my advisees off, don't run away, guys. Anyway, it is good to help you understand how statistics work. It can help you with reading statistics as it goes along. And just think of it as, I'm not trying to make you fluent in it, but just try enough of the language to sort of parse out what happens when things show up. Cool? All right. So we're going to start with a data example. It is, of course, in R. And of course, I thought I had started it up. But you know, in my long string of failures that is on display in this class with this homework system, I'm able to just not have it be that way. But here, here's our data. It's in the EPSY 905R package, and it's pretend that I have 1,000 students SAT math and verbal scores. I actually don't have them, but let's just pretend. Okay? I made these data up long time ago, actually. But here you see we have the mean for SAT verbal and SAT math. We have their standard deviations, and we have the correlation matrix. Cool? All right. There they are. I even made them up so they would be like the 10-point increments that SAT used to be. But around here, of course, it's ACT, right? How many of you took the SAT? Oh, most of you. Never mind. Okay, ACT only? Anybody? Fair enough. Yeah, I never took the ACT, and I only barely made it to the SAT on time. I kid you not. I have this water glass that keeps losing its straw. So I take a drink, and it's like, ha! It's like the Peanuts cartoon with the football and whatnot. Like, I can hear the water. I'm salivating for it, and then when I go for it, it's just completely dry and empty. It's kind of humorous. Anyway, let's type more definitions, shall we? Any questions as we go on? I'm trying to make this more conversational and less dry, because this is pretty dang dry. Let's just be honest, right? All right. So, a matrix is a rectangular array of data. We store numbers in it. There. This, sit next to the iPad. Move this screen out of the way so I can see the upper front part of the class. There we go. Now I can see everybody. That's good. Hi, Ina. All right. Or maybe you wanted to be hidden by the screen. I'm sorry. It's a box of numbers, as I mentioned, right? So if you look down here at this thing right here, we have all of our data in something that has brackets on the outside of it. Now, that box, we're used to boxes that are in 3 dimensions, right? But technically speaking, a matrix can have any number of dimensions. We're not usually going to see those matrices. Right? We typically are going to deal with data matrices that only have 2 dimensions. And those dimensions we're going to label. One dimension is going to be the row, and one dimension is going to be the column. So rows move vertically, up and down, and columns are moving horizontally across the matrix. All right? Typically, the way that we notate, again, this is language, this is alphabet, when we symbolize a matrix in text, when we're typing something, is with something that's in boldface. And often in a capital boldface letter. So it's like saying it's X. Right. Like, you know, I saw our president tweet last night in all caps. Right? Imagine if you could boldface that. That would take crazy, sorry, I'll just say it. That'd take crazy to a new level, right? Like if you can tweet in bold and caps, I don't think you can, right? So, again, not all political views are welcome here, but I still have my own right to my own, and I'm not trying to tell you how to believe. Hold off on that. But seriously, though, right? It's like you see that text speak where you're capitalizing thing, it's screaming at someone. What is bold on top of that, right? Right? It's yelling. And typically we describe a matrix by its size. And size, in this case, is very important because we need to understand in which position matrices have to align to make certain operations happen. So we have to sort of keep track of how many rows there are, how many columns there are. So we would often say that X is something that's size R by C. And sometimes you put that in lower in the subscript. When I handwrite a matrix, I usually put half an arrow at the top, and that's because it's very hard for me to boldface my handwriting. Of course, it's very hard for me to do any handwriting, so bear with me on that. Okay? So far, so good? All right, now here's an integral. No, I'm just kidding. Let's just keep going into it's just simple integration, right? By the way, that's the other thing. If you're ever describing, if you're one of the people who are going to go into a stat field and do quantitative data a lot, try to never use the word, it's simply this or obviously. You sort of catch yourself because there's certain things when you learn, you can't unlearn them. You can't unsee things before. But it may take you years to figure things out. And then all of a sudden, it's obvious, right? So, but I've learned it's very off-putting to the listener if I'm saying this is obviously just a matrix inverse, right? It doesn't, that, by the way, describes most of my field and my graduate training. Oh, this is obviously that. Yeah, you moron, why don't you learn this, right? Anyway, that's what it sounds like. So, pardon me if I ever say that. But a matrix is, oftentimes, if we have one of the dimensions of the matrix equal to size 1, we have a special name for that type of matrix. It's called a vector. Cool. Before I got into matrix algebra, I used to think vector was only something you listen to in science fiction movies or whatever. I'm not a real big science fiction fan, so I was like, I don't ever hear vector in baseball or sports, but that was what I was into back in the day. But no, vectors are everywhere. So for instance, if you have a 1,000 row by 1 column matrix, we would call that a column vector. Right? Or alternatively, a 1 row by 2 column matrix would be a row vector. Right? So it's basically, by saying column vector, you're implying that the second dimension has is only one of those. And alternatively, a row vector would say the first dimension, there's only one length of 1 for it. And oftentimes, we denote vectors using the same boldface, but we use lowercase letters for them. So they're not as angry as matrices. Not as crazy as matrices? I don't know. These things are lowercase letters. Also, I would note there is a dot. That dot represents sort of everything that's not shown. So for instance, x dot 1 says all of the rows but the first column, right? And x1 dot says all of the columns in the first row. So it's sort of the aggregate of what we do. And actually there's analogs to everything I'm saying with that in R as well. I'm about to show this to you, so hang in there. There we go, there's units of aggregation. There we go. Sometimes what you'll find is that these rows and columns get separated by the comma. So sometimes in text you might see x1, 100 or 1000. That represents, kind of I haven't gotten there yet what that is, but that comma really splits the numbers. You quickly run into issues if one of the indices has double digits. You can't tell what's a single digit number and what's a multiple digit number, so the comma tends to separate the spots, row versus column, sometimes. So what does a matrix consist of? What does a vector consist of, right? A matrix or vector is comprised, I think, not composed, of a set of elements. So each number in the box is called an element of a matrix. In fact, everything that you knew about the number before you talk about matrices is an element, right? It's just the element. It's a specific value itself. So our X matrix, which had 1,000 rows and 2 columns, each element is denoted with just a regular lowercase unbolded character. In this case, lowercase x, no bold. And we often tell the position of the element using the subscripts of x. Right? So I and j represent what number in the box that comes from. The first position would be the row index, and the second j would be the column index. So if we were to pick the second, this data point right here, well, we can see it's in the second row, 1, 2, and it's in the second column. So it gets the value x2, 2, which sometimes gets separated with a comma. Fair enough? Cool. And all the things I'm talking about here, again, everything I'm saying to you right here, this is already implemented in matrices in R, and actually if you're using other software packages, MATLAB, I don't know if anybody uses MATLAB around here, it seems to be pretty popular. It's all about matrices, so it all works. So oftentimes, those individual elements, when they're not in a matrix, although there's a sort of the philosophical issue of what makes a matrix, and a scalar has to be a 1-by-1 matrix, but hold off on that. A number outside of a matrix is called a scalar now. Everything we called a number before, it's a scalar. It's got its own term. You didn't know you were working with scalars, did you? No. What does the term scalar represent? I will answer my own question. The name, by the way, I have this, I watched this show with my wife called So You Think You Can Dance. Have you seen that show? And there's a judge on there named Mary Murphy, and she sort of answers her own questions as we go. So we have this drinking game. Whenever she asks a question and answers it herself, we have to drink. So I just did that. So anybody who's got a beverage, please go ahead. It's bottoms up. What does a scalar mean? Well, I'll tell you. It's interviewing myself here. You can think of it as a number that sort of scales a matrix. The word scale has interesting connotation. It certainly means something in the measurement field, but really it's the idea that it provides kind of a unit of distance, right? So we might be able to take, if we multiply a vector by a scalar, it actually makes it longer. If the scalar is bigger than 1 or smaller than -1. It can also make it shorter if it's a fraction. But typically our scalars are written without bold face. You can think of each element of a matrix as being a scalar, although they don't exactly work like that when it comes to multiplication entirely. But they sort of work like that. Okay, let's go into, so those are our definitions. Let's go into our first operation on a matrix. You ready? Here we go. What do you think the transpose means? Changes it?
Change rows.
Exactly. A transpose of a matrix, if your box was long and skinny before, it becomes short and wide. It basically tilts it. So here we had a 1,000 row by 2 column matrix X. The transpose, I like to denote transpose with a capital T in subscript. Sometimes you see it with a prime symbol, but a lot of times I do work where we take derivatives of matrices, and that typically takes other symbols as well. So T, I feel like, is a very literal version for transpose. What the transpose says is you take the rows, the columns of the previous matrix, and they now become the row position, and the row position now becomes the column position. Or a better way of putting it, each element, xij, in the original matrix is now the element xji. You've switched the row for column. So let me show you this a little bit. Let's take this 580 there. What is its row index? It's in row number 1, drink. What is its column index? 1, 2. All right, so this would be x1, 2 in the original matrix. You'll note now in the transpose matrix, it is in row 2 and column 1. Right? So for every number in the matrix, we've just literally switched row and column. Now, why would you want to switch that? What was wrong with the box and the way I had it? Sorry. And I sound like I'm talking to my son. Why are you doing that? No, we don't try to... Never mind. Potty training has been an ordeal. Yes. Oh, I sometimes separate the position of row and column with a comma, mainly because when you get up to, like, if we did x10 and 1, like row 10, column 1, it's hard to tell if that's x101 or x101, so I usually make a comma in between to say row separated from comma in the notation. Not everybody does that. And again, you know, my notation is not like everybody else's, so we all have our own way of notating things. But why on earth would we want to take a transpose? Generally speaking, matrix transposes keep the same information in the matrix, but they help us align matrices better to do the work that we want them to do. In particular, when we get to matrix multiplication, you're going to see that only some matrices can multiply other matrices. And yet, if we are able to transpose matrices, we might get that to work. So that's why we have a transpose in the first place. How are we doing so far? Pretty good? There are types of matrices. A square matrix. It's a box that looks like a square. Same number of rows as it has columns. You've seen square matrices before, I take it. You've seen a correlation matrix, right? You've seen a covariance matrix, or at least we talked about them. Those are square matrices. A diagonal matrix is a matrix that only has numbers along the diagonal, and it has zeros in the off diagonal, right? So a diagonal matrix has to be a square matrix for it to be diagonal. Otherwise, there is no diagonal. You sort of get cut off somewhere with a rectangle, right? we end up seeing these diagonal matrices a lot in statistics whenever we want to move from covariance to correlation. There's a quick way to do so with matrices, and the way we do so is with diagonal versions where the diagonal has the standard deviation of each variable in it. Right? So it makes things quickly change. And then finally, a symmetric matrix is a square matrix, again, where the lower triangle of the matrix, this is the part that's below the diagonal, is identical or reflected across diagonal with the upper triangle. Or put more mathematically, where every element xji is equal to every element xij is equal to xji. I was reading backwards. Right? So this spot right here, this is our A 2, 1 right here. You would expect A 1, 2 to be the same. Cool? Symmetric matrices help a lot of things because there are certain features. They add additional features to the matrices that make some of the computations easier to understand. But that's about it. But we see them all the time because we deal with covariance and correlation almost all the time in multivariate statistics. Everything okay? Cool. Let's get into vectors then. Vectors can actually be represented as lines on a kind of a coordinate system. Now, this is the part of the class where some of you are like, I totally get the visual geometry, and some people are like, I totally hate the visual geometry. I feel like there's two large camps of people. I'm more in the I hate it, but I'm going to try to describe it to you because I feel like there's predominantly more people are more the visual. So I just want to show you what's going on. It allows us to put some literal meaning to it. But if we have the vector A here, that has, is this a row or a column vector, by the way? It's a column vector. It has 2 rows and 1 column. Right? And B is also a column vector. We could go plot the rows, element 1 of row 1 over here on an x-axis, row 1, and we could plot row 2 on a y-axis, and we'd end up with these 2 dots, right? This is A right here, and this is B. Right? Does that make sense? So with that, though, we could actually talk, why we might want to plot those is because when we put them on a number system, we put them in a space like this, now we can derive lengths of them. We can talk about angles between them. And sure enough, a lot of those terms, lengths and angles, actually mean something in statistics that you've never heard of before. So you may have never heard of it before. Right? So we're going to define some of the terms that we know in statistics this way. So here's the question for you. Well, how could we plot a column vector for each of our example variables? How many dimensions would we need? I'll be more specific. I don't think we can plot it. Maybe someone can. We could certainly plot the row vectors. Right? Each row vector, because there's 2 columns, we can put column 1 and column 2 on a graph and have a scatter plot. But if we're going to plot the column vectors, those are 1,000 by 1 vectors. And mapping on here, each row represented the dimension. We need a 1,000-dimensional space to map them to. I don't know what that looks like. But I can tell you a 2-dimensional space is nice and flat. And I could probably talk about a 3-dimensional space pretty well, right? So we could have this literally a cube would be 3 dimensions. And somewhere in the middle, we'd define a 0 point, right? And you can see these going off into space. So the 1,000-dimensional vector could be thought of the same way. If we had a 1,000-dimensional box, somewhere in that box there'd be a 0 point, and the end of that vector would be off wherever else, right? So that'd be really hard to conceptualize, but that's what's happening. It's one way that you can conceptualize what we do with data, actually. But what we can do with this, though, is we can talk about the length of a vector based on how far a point is away from 0. So here comes a flashback to math classes I took in college. Do you remember how we'd find the length of something like that? That's right. We use the Pythagorean formula, the Pythagorean theorem, to figure out when we form a right triangle, right? We could figure out what that happens to be. And sure enough, that's where we get our length. The length of a vector is given by the square root of the squared sum of each of its elements. Right? Oftentimes, length is denoted with 2 lines. I don't know what you call that, like X in jail or something. Like when you're angry X, you go to jail or something like that. I don't know. But that's the length of X. I will also note that this version of distance is actually called Euclidean distance. There's actually many, many other versions of distance out there. But this is only one of them. It's the one that makes a lot of sense because we often use it in other spaces that we do. So we can see that from the last slide, the length of X would be, length of A would be 1 squared plus 2 squared, or 1 plus 4. The square root of that is 5. So the length of A is 2.24. The length of B is 3.61. And similarly, we could talk about the length of our variables in our data. Those vectors that are off in the 1,000-dimensional space from a 0 point, here's their lengths. 15,868.138, 15,964.42. That doesn't seem to have much meaning, but sure enough, if we were to have gone instead of using our data, if we mean-centered our variables, now we're going to talk about this. Mean-centering it means it'd be x minus x bar squared, the sum of those things. And now that starts to make a little bit of sense if you remember statistics formulas, because that's the kind of the numerator that goes into variance or standard deviation, right? So you can think of this as a very crude analog to a standard deviation. It's still not standard deviation, it's still not variance, but you can see where we're getting the idea from, right? So what we're talking about is really long things, vectors that are really long. If we had a data set that had a really long vector, that'd be something with a lot of variation to it. Something that's really short would be something with little variation to it. Kind of a different way of looking at data. How we doing? All right, I promise I'm going to give you a break in just a couple minutes. We're going to have 2 breaks today, unlike the last week. Now, what we can do with vectors, we can add them together. We can do this with matrices too, but we're going to add them together. Vectors to be added together have to have the same number of rows, and the same. Actually, any matrix to be added together has the same number of rows, same number of columns, right? So here, these are all 2 by 1 vectors. So when we add them together, the sum of the vectors is just the sum of each of the respective elements. So 1 plus 2 is 3, 2 plus 3 is 5. Sure enough, this has a geometric meaning, but real quick, we do this all the time in data. We could create SAT total by summing the 2 column vectors of SAT. But this is what happens geometrically, right? If this was our 0 point here, here's vector A and here's vector B. When we add them together, it's like appending the end of the vector with the other one. And the sum is given by the spot that appending ends up at is actually equal to the length of the new vector, right? So it has a nice geometric meaning to it. Furthermore, what we can do is we can multiply these vectors by a scalar. We can imagine we take a new vector D and we take 2 times A. The scalar multiplication works by taking the scalar and multiplying it by every element inside the vector. Works the same in matrices too. So 2 times 1 is 2, 2 times 2 is 4. And sure enough, when we multiply by a scalar, we change the length of the vector. If we take 2 times it, it actually makes it 2 times the size, right? So this is sort of how it works. Here are our 2 original vectors. Here's where 0 is, the top left. Multiplying them by the constant a when a is bigger than 0 brings about a lengthening of those vectors, stretching them out. Okay, last topic, then we'll take a break. We can also take what's called a linear combination of our vectors. You've seen this before. We talked about linear combinations in the linear model. y equals beta 0 plus beta 1x plus beta 2z, that thing. Same thing happens with vectors. We have x1, x2 all the way through xk. We could weight each of them with a number, a1 through ak. This is a scalar, right? And we can sum them together to form a new vector y. This is the basis for what we do in everything we do in linear models. Oftentimes, this also speaks, it's going to become clear why we might do this quickly when we do linear models. It also shows up in principal components analysis. But generally speaking, you can see the similarity of regression, right? That's sort of what we're doing. This is how we make a predicted value. So now you're starting to think, wait a minute, if I did, remember, so as you're on break for 10 minutes, I want you to ponder, or actually don't, do whatever you like. But if you have a chance to think, out there a little bit, if we saw vector addition as something like this, what's going on in a regression? If we have these, if all the x's are a bunch of column vectors, we're adding things together, what's going on in regression when we make y, or make the predicted value of y? We'll talk about that when we come back. How about we take 10 minutes, come back a little bit at like 4:33 on that clock up there, or sorry, 2:33. Come back at 4:33 and I won't be here. See you soon. You see, it's just, all this class is like my failures on display for everyone. So humbling.